This is Swathi from Department of Chemistry, K.B.N college. Now today we will discuss about the carbonyl compounds. So first let us discuss what is meant by a carbonyl compound. So carbonyl compounds means the compounds, these are also organic compounds containing carbon and oxygen as the major elements, and in between the carbon and hydrogen they contain double bond. So those are called as a carbonyl compounds. So if in any organic compound, if you found C double bond O, then that functional group is called as carbonyl compound functional group. So depending upon the nature of the substituents, these are classified into two types. Carbonyl compounds are of mainly two types. So number one is aldehydes and number two is ketones. So carbonyl compounds in which carbonyl group is bonded to a carbon and hydrogen are known as aldehydes. So once again I am repeating, carbonyl compounds in which carbonyl group is bonded to a carbon and hydrogen are known as aldehydes. If in second case is ketones. In this case the carbonyl group is bonded to the carbon atoms are known as ketones. So the basic difference between aldehydes and ketones is, in case of aldehydes, carbonyl group is bonded to the carbon and hydrogen, whereas in case of ketones, carbonyl group is bonded to carbon atom only. So that is the basic difference between the aldehydes and ketones. Next, let us discuss about the nomenclature of carbonyl compounds. How carbonyl compounds are named. So according to IUPAC nomenclature, in case of aldehydes, in common systems, aldehydes are named after the name of the compound produced by the oxidation of the aldehyde. In IUPAC system, the final letter E of the parent aldehyde is replaced by the word Al. So again I am repeating, in case of IUPAC nomenclature, the compound which is obtained by the oxidation of the aldehyde is, in that compound the final letter E will be replaced by Al. Hence let us see one example, that is for formic acid, that is HC double bond OH. The common name of this one is formaldehyde. The common name of this one is formaldehyde. HC double bond OH is formaldehyde, and the IUPAC name is methanol. And the second one is CH3 C double bond OH. The common name of this one is acetaldehyde, and IUPAC name here last letter is replaced by Al. Actually, in case of acetaldehyde, so acetaldehyde on oxidation it gives next, in case of propanaldehyde, the common name is propanaldehyde and IUPAC name is propanol. Whereas in case of aryl aldehydes, the hydrogen atom is replaced by the phenyl group, that is benzaldehyde. There is no common name, IUPAC name for this compound. So let us come to the ketones. In common systems, ketones are named by attaching suffix ketone to the name of the alkyl or aryl group attached to the carbonyl carbon. In IUPAC system, final letter E of parent alkane is replaced by word ONE, and position of the carbonyl group is indicated by lowest possible number. So here let us take one example, that is which is called as a dimethyl ketone. The common name is dimethyl ketone. The formula is CH3 C double bond O CH3, and the IUPAC name of this compound is 2-propanone. And second example is ethyl methyl ketone. Here the formula of ethyl methyl ketone is C2H5 C double bond O CH3, and the IUPAC name is 2-butanone. Whereas in case of propanaldehyde, the IUPAC name is propanol. So this is about the nomenclature of ketones. So overall, in case of aldehydes, the oxidation product of organic compound is the final letter in that compound. The name of that oxidation products of organic compound, the final letter E will be replaced by Al. Whereas in case of ketones, the final letter E of the parent alkane is replaced by the word ONE. That is the basic difference between the nomenclature of aldehydes and ketones. Once again I am repeating, in case of aldehydes, the final letter E of the parent alkane is replaced by Al, whereas in case of ketones, the final letter E of the parent alkane is replaced by the word ONE for ketones. So according to the IUPAC name, the corresponding names are given to each and every carbonyl compound, whether they may be aldehydes or ketones. So let us discuss about the some of the properties of the carbonyl compounds. So the one of the best property of carbonyl compound is they undergo aldol condensation and gives a compound called aldol. So aldol condensation means it is a base catalyzed condensation of aldehydes or ketones having alpha hydrogen atoms to form beta hydroxy aldehyde, which can also be called as a aldol, or beta hydroxy ketone, which can also be called as a ketol, is called as a aldol condensation. So what is the first necessary condition for a compound to participate in aldol condensation is a carbonyl compound, whether it may be aldehyde or ketone, it must have the alpha hydrogen. Those compounds who are having the alpha hydrogen are able to participate in the aldol condensation and forms a resultant compound called as a aldol. Here the resultant compound is aldol, hence this reaction is called as a aldol condensation. So let us see the once we look at here the reaction. So here two molecules of acetaldehyde and condensation in presence of base, they have formed a beta hydroxy aldehyde, which is called as a aldol. So we will discuss about the mechanism behind this aldol condensation. So it involves mainly three steps. In the first step, alpha proton abstraction of aldehyde from base to form corresponding carbanion. So the first step in the aldol condensation is formation of carbanion from the one molecule of aldehyde. So here one molecule of acetaldehyde, here it contains alpha hydrogen. This alpha hydrogen is abstracted by the base which contains OH minus ions, and it forms resultant carbanion, that is CH2 minus C double bond OH. In the second step, the resultant carbanion, which can also be called as a nucleophile, attacks the another molecule of aldehyde to form anion. So the second step is the nucleophile attack of the carbanion on carbonyl carbon of second molecule of the aldehyde to form anion. Here in this step, carbanion will attacks the C double bond O group, which is present in the another carbonyl compound, and forms a negatively charged anion. The third step is the protonation of the anion to form beta hydroxy aldehyde. Here protonation means addition of H plus ions. So in the third step, finally the anion which is formed in the second step undergoes protonation. It results in the formation of a beta hydroxy aldehyde, which can also be called as a aldehyde. So this is about aldol. So this is about aldol condensation. So aldol condensation means the condensation of 2 moles of aldehydes or ketones to form corresponding beta hydroxy aldehyde or beta hydroxy ketone is called as a aldol condensation. In this case, the main condition for the participation of the aldehydes or ketones in this reaction is, first of all, it should have the alpha hydrogen. So that is the necessary condition for the formation of participation of the aldehydes or ketones in the aldol condensation. So in this step this mechanism involves 3 steps. In the first step, formation of carbanion takes place. In the second step, attack of the carbanion to the another carbonyl compound takes place. In the third step, protonation of the anion to form the beta hydroxy carbonyl compound takes place. So the second property of the carbonyl compounds is they participate in reduction reactions. That is, one of the most available reaction is Clemmensen reduction. Aldehydes and ketones are reduced with zinc amalgam in presence of concentrated hydrochloric acid to form corresponding alkanes. It is called as a Clemmensen reduction. So once again I am repeating, Clemmensen reduction means aldehydes and ketones are reduced to corresponding alkanes in presence of zinc and mercury amalgam and in the presence of hydrochloric acid. This reduction is called as a Clemmensen reduction. Let us take one example. Here in this example, esteraldehyde is reduced to ethane in presence of zinc amalgam and hydrochloric acid, resulting in the formation of water molecules. In the second example, here acetone is reduced to propane in presence of zinc amalgam and hydrochloric acid, results in the formation of a propane with the elimination of water molecule. Here reduction means addition of hydrogens. So by the addition of hydrogens, esteraldehyde is converted into ethane and acetone is converted into propane. In the same way, remaining aldehydes or ketones can also be converted into corresponding alkanes depending upon the participation of the aldehyde or ketone. And the second reduction reaction is Wolff-Kishner reaction. So reduction is common for all the things. Reduction means addition of hydrogens. So here in case of Wolff-Kishner reductions, aldehydes and ketones are reduced to corresponding alkanes in presence of strong bases like sodium hydroxide, potassium hydroxide and hydrazine. So the variation between the basic difference between the Wolff-Kishner reduction and Clemmensen reduction is, in case of Clemmensen reduction, the reducing agents are zinc amalgam and hydrochloric acid, whereas in case of Wolff-Kishner reduction, the reducing agents are hydrazine and strong bases like sodium hydroxide and potassium hydroxide and in presence of alcohol. So that is the basic difference between the Wolff-Kishner and Clemmensen reduction. In both the cases, the resultant compounds are alkanes only, but only they differ in the reducing agents. So let us take one example for Wolff-Kishner reaction. Here I have taken the acetaldehyde. This acetaldehyde on reaction with hydrazine, that is NH2 on boiling with hydrazine, it is converted into corresponding hydrazone. This hydrazone on reaction with sodium ethoxide, that means which is a strong base, simply with the elimination of nitrogen it forms a corresponding ethane. So second example is, here I am taking ketone, that is acetone. This acetone on reaction with hydrazine, it forms a hydrazone, which is on reaction with sodium ethoxide, it has formed propane with the elimination of nitrogen. In the same way, remaining aldehydes and ketones are also reduced to corresponding alkanes with the elimination of nitrogen in presence of hydrazine and strong bases and alcohols in case of Wolff-Kishner reduction. So third one is reduction in the presence of lithium aluminum hydride or sodium borohydride. So in this case, the reducing agent is lithium aluminum hydride or NaBH4. Here, in the presence of lithium LiAlH4, aldehydes or ketones are reduced to corresponding alcohols. Once again, I am repeating, in the presence of LiAlH4 and NaBH4, aldehydes or ketones are reduced to corresponding alcohols. So here I have taken the example of acetaldehyde. So acetaldehyde, by reducing acetaldehyde in the presence of lithium aluminum hydride as a reducing agent, it is simply converted into alcohol by the addition of hydrogens. In the same way, acetone is converted into isopropyl alcohol by the addition of hydrogen. So the basic difference between the Wolff-Kishner reduction and Clemmensen reduction and a reduction with lithium aluminum hydride is, in case of Clemmensen reduction, the reducing agent is in zinc amalgam and hydrochloric acid, whereas in case of Wolff-Kishner reduction, the reducing agent is hydrazine and bases like sodium hydroxide or potassium hydroxide and alcohol. But in these two reactions, that means in case of Wolff-Kishner reaction and Clemmensen reactions, the products are same, only they differ in the byproducts. In case of Clemmensen reduction, the byproduct is water, whereas in case of Wolff-Kishner reduction, the byproduct is nitrogen. And in the third case, that is the reduction in the presence of LiAlH4 or NaBH4 results in the formation of a corresponding alcohols. So these all are the properties of the carbonyl compounds. One of the important properties, aldol condensation, that means they participate in condensation reactions and gives corresponding aldols or ketols. Second property is they participate in reduction reactions and they give corresponding alcohols and alkanes respectively depending upon the reducing agent which is used in the reaction. Now let us discuss about the one more topic, that is active methylene compounds. So here first we will know what is meant by active methylene group. So if a methylene group is attached on both the sides by electron withdrawing groups like CHO, CO, COH or COOR, CN or halogens etc., then it becomes highly reactive. So this group is commonly known as a active methylene group. So once again I am repeating. So active methylene group means if the methylene group is attached by either CHO or CO, COH or COOR or cyanide CN or halogens on both the sides, then it becomes more reactive. Hence that group is called as a active methylene group. The compound containing active methylene group is called as a active methylene compounds. So the best example for active methylene compounds is acetoacetic ester, that is which is also called as a ethyl acetoacetate. Here methylene group, that is CH2 group is surrounded on both the sides by COO and CO. Hence this methylene group, that is CH2 group, is called as a active methylene group. Since it is attacked by CO and COO on both the sides, this compound is called as a active methylene compound. In the same way, another example for active methylene compound is diethyl malonate, that is CH2COO C2H5. CH2COO C2H5. In this case also CH2 group, that is active methylene group, is surrounded on the both the sides by COO C2H5 and COO C2H5. So active methylene group means a methylene group which is attached on both the sides by electron withdrawing groups like CO or COO or cyanide or ester or acids or halogens etc. is called as a active methylene group. And if a compound contains active methylene group, then that compound is called as a active methylene compound. Best examples for active methylene compounds are ethyl acetoacetate and diethyl malonate. So let us discuss about the preparation of active methylene compound, that is acetoacetic ester. It is usually prepared by K.B.N condensation, which can also be called as a K.B.N ester condensation. So in this process, an ester having alpha hydrogen atoms combined with another molecule of same or different ester in presence of a strong base to form beta keto ester. It is called as a K.B.N condensation. So once again I am repeating, in case of K.B.N condensation, an ester which is having a alpha hydrogen undergoes condensation with same or different ester in presence of strong bases like sodium hydroxide or potassium hydroxide and in presence of alcohol, and results in the formation of a beta keto ester. That beta keto ester is nothing but our acetoacetic ester, depending upon the initial reactants. That reaction is called as the resultant compound, that is beta keto ester, is called as this reaction is called as a K.B.N condensation. So let us take one example. Two molecules of ethyl acetate are combined in presence of sodium ethoxide to form ethyl acetoacetate or acetoacetic ester. Here let us see the example, that is ethyl acetate. The formula of ethyl acetate is CH3COO C2H5, and it reacts with the another molecule of ethyl acetate in presence of strong bases and alcohols. Here strong base and alcohol together reacts with and forms a sodium ethoxide. This sodium ethoxide, in presence of this sodium ethoxide, the two ester molecules undergoes condensation and results in the formation of a acetoacetic ester. Let us discuss the mechanism. So this mechanism mainly involves three steps. So before going to the mechanism, first the sodium ethoxide, which is formed by the reaction between the strong base and ethyl alcohol, that is sodium ethoxide, undergoes decomposition to form Na plus and C2H5O minus. So in the first step, formation of carbanion from the acetoacetic ester takes place. So here CH3COO C2H5, which is our ester, reacts with the sodium ethoxide ion, that is C2H5O minus, by the abstraction of alpha hydrogen from CH3COO C2H5. It is converted into carbanion with the elimination of alcohol. Here the carbanion formed is CH2 minus COO C2H5. Here the CH3COO C2H5 will reacts with the ethoxide ion, that is C2H5O minus. This C2H5O minus will abstract the alpha hydrogen, that is CH3COO C2H5 from CH3COO C2H5 and forms CH2 minus COO C2H5 and gives alcohol as a byproduct. In the second step, attack of carbanion on carbonyl carbon atom of the another ester molecule takes place. So in the second step, this carbanion which is formed in the first step will attacks the carbonyl group of the another ester molecule, which results in the formation of a anion. In this third step, removal of ethoxide ion from the anion takes place, results in the formation of a beta keto ester. So this reaction is called as a Claisen condensation or Claisen ester condensation. So Claisen ester condensation is mainly for the preparation of the ester ester. Here that means ester ester is a active methylene compound. For the preparation of active methylene compounds, we are using the Claisen condensation. So in case of Claisen condensation, two ester molecules undergoes condensation reaction in presence of strong base and alcohol, results in the formation of a beta keto ester, which is a active methylene compound. So this reaction is called as a Claisen ester condensation. So this mechanism mainly involves three steps. So first step is the formation of carbanion. So in the first step, the ethoxide ion which is generated during the starting of the reaction, that is C2H5O minus, will abstract the H plus ion from the one ester molecule, that is CH3COO C2H5, and forms a carbanion, that is CH2 minus COO C2H5 with the elimination of alcohol. In the second step, attack of carbanion on carbonyl group of the another ester molecule will take place, results in the formation of a anion. In the third step, removal of ethoxide ion from the anion will take place, results in the formation of a beta keto ester, that is here ketone group is present in the beta carbon atom, hence it is called as a beta keto ester. This beta keto ester is nothing but our active methylene compound. In this compound, methylene group, that is CH2, is surrounded on both the sides by one side it is surrounded by CH3 C double bond O, that is another side it is surrounded by another electron withdrawing group, that is COO C2H5. So this is about the active methylene compounds and their preparation.